Okay. So the topic is, so today lecture what I will be doing, I will not go through the how to solve the questions, rather I will just give an introduction about ordinary differential equations. You might have covered that already in some courses, but I'd like to put this into perspective from our engineering background, where this topic fits in us as engineers. So, as we know, the derivative, generally speaking, captures the rate of a change of function. So when we say differential equations, so these are equations that contain derivative, and this derivative again capture the rate of a change of function or functions. Now, you see that depending on the system that we are trying to solve, we will have different number of differential equations. Now, when we talk about linear equations, we said that, okay, we need the number of equations to be equal to the number of unknowns that we have on our system. Here, when we deal with differential equations, the number of differential equations should be equal to the number of energy storage elements. Any storage element in your system will need one differential equation to govern it, to describe it. So if I have 2, 3, 4 storage elements, then I will need the same number of equations to be able to solve. So let me just give you an example. Let's start with our favorite, the electrical system. So in this system, we have 2 capacitors and 1 inductor and 1 resistor. The resistance is not a storage element. The resistance is a dissipation element. So this one we don't care about. So we have here 2 capacitors and 1 inductor. So it means that I will need here 3 differential equations to be able to solve such system. When you look to the mechanical system, it's the same thing. Here we have a mechanical system that is composed from 2 masses and a spring, and there's a force in that direction. Now, the 2 masses are storage of kinetic energy, and the spring is a storage of potential energy. So here also we will need 3 differential equations to be able to describe the system. Could you post the notes for the material we are dropping for future reading? Yes, I can do that. And thanks for asking. So I will do that. I will post it. And if I forgot, please just remind me by an email. That's the spirit. Good. I mean, if you want to read even something that we did not cover, that's really, really good. Okay, so let's move on and have more specific examples. Okay, so here in this example, we have, this is something you covered in circuit. So we have here a switch, okay, and we have a current source. So this switch at t<0 was closed. So we have this circuit running. So this is fully charged. And then we will have the switch open. So this is the circuit now at t equal or greater than 0. So if we take a KVL here, so we have LdI by dt plus Ri equal to 0. So we have here 1 unknown, which is the current, and also 1 differential equation because we have only 1 storage element. So if we come here, so now we have 2 storage elements. We have the inductor and we have the capacitor. So if we take a KVL, R times I, the voltage across the inductor, LdI by dt, plus the voltage across the capacitor, which is V of t. So this is 1 differential equation, but it has 2 unknowns. It has the voltage and it has the current. So still, I will need another differential equation to be able to solve this. And the equation for this is I of t is equal to C dV by dt. Now, yes, I can change this into a second order differential equation, okay? So either I will have 2 differential equations with 2 unknowns, or 1 second order differential equations. In both cases, I can solve the system. Now, if you look to the mechanical system, the same thing. So the force as we know that when you have a force on a mass, and this mass is going through a velocity, okay, we know that the force is equal to ma. Is one of the basic motion laws. Okay, so here assume there is a friction roller, so there is no force in this direction, just one force in that direction. So the force is m, which is the storage element that we have here, the mass, and times dv by dt. So here we have only one differential equation because we have only one storage element. Now, if I add friction, and so we have here an opposing force, okay, but friction is not a storage element, it's just another force or another form of a force in a different direction. So when I write the equation, so I will need only one differential equation. So the applied force minus the force that resists this is equal to, again, mdv by dt. Now, if I move from that system and I will start to have a spring now, so I'm applying a force in this direction, still we have the friction, but also the potential energy that is exercised by the spring is also there. So now I will have two storage elements, the spring and the mass. Okay, so here the force minus the friction, okay, minus k times x of t equal to mdv by dt. So we have here x of t as the displacement, and we have dv by dt, which is the rate of change of the velocity or the acceleration. So here I have, so this is the force exerted by the spring. So I have here one differential equation, but I have two unknowns, the displacement and the velocity. So, but we know that the velocity is nothing but dx by dt. So again, I will have here two differential equations, or I can have one differential equation, but to be a second order differential equation. And this, what I just mentioned, doesn't just apply to electrical or mechanical systems, okay? So it can apply also to many things, for example, on thermal system, fluids, etc. So whenever we have a storage element, for example, here in thermal systems, we have storage elements like masses that store the temperature and release it later on, okay? So again, we will encounter the same phenomena, that the number of differential equations needed to be able to model the system is equal to the number of storage elements. So after this introduction, let's now move on to differential equations. So we realize that differential equations are extremely important in engineering systems, and many engineering systems are modeled as differential equations. And actually, this is one way to model a system. And you will study later on in signals and systems, in control theory. I think those, especially those who go for ELE, you will study more about modeling of a system. If I have a system, how to model that system, and you will understand, or you will know later on, that one way to model the system is use the time domain approach or the differential equation approach. Now, for the differential equations, there are two different types of derivatives that encounter, and hence you will have two different types of equations. The first one, which is the ordinary derivative, which is the normal one, like let's for example dv by dt, which is the acceleration, or dx by dt, which is the in this case is the velocity. Okay, so v, or the unknowns, is only a function, or all of them, for example here, dx, is all of them are a function of only one independent variable, which is in this case, this is the time. Okay, so as you have seen in the, we could have like multiple derivatives, but all of them are with respect to one independent variable. However, if we have more independent variables, for instance, if I have let's say I have an x and I have a y here direction, and I have something that is moving in the xy direction with time. So then I will have the derivative with respect to the y direction, and I will have the derivative with respect to the x direction. Okay. So in this case, so I'm looking here from the top. Imagine I have an object that is moving in the xy direction. So it will have a derivative, or we call it partial derivative, because here we have more than one independent variable. Okay. So this is what we call the partial derivative, and this is how we write it. Okay, so this notation for the partial derivative. Now, in this course, we will be dealing only one derivative, but the approach is exactly the same. There's not much difference in the approach, but we will deal only with ordinary differential equation, or what we call ODE. So this is as an example here. We have the ordinary differential equations, okay, and here it could have one or more ordinary derivatives, but as I said, you have only one variable. On the other hand, here this is an example of a partial differential equation, and here you can see here clearly that you have two independent variables that you are taking derivative with respect to. So this is what will be covered in this course. Now, here the ordinary differential equations, for example, this equation dv by dt minus dft equal to e of t. So you could have, there's the number of unknowns here. You could have one or more ordinary derivatives of unknown functions with respect of one independent variable. I'll just mention that this is a second equation as well. So here the unknown that you have is x of t. So this is first derivative or second derivative. So your unknown, the one that you want to find, is x of t. And t is your what we call the independent variable. This is the variable that you are taking the derivative with respect to. Now here the order, if I say what is the order of the differential equation? Okay, is it first order, second order? How we decide the order of a differential equation? So we see what is the highest order of derivative. Okay, so for example here, this is the highest order of derivative, first derivative. Here is the second derivative. Here is also second derivative, because this is just taking the cube, but the derivative itself is second derivative. So here it is first order, second order, and this is second order ordinary differential equation. Now, the ordinary differential equation could be linear equation. So what do we mean by linear? Okay, the unknown function and its derivative. So the unknown function, this could be x of t, b of t, and its derivative, all of them appear to the power of 1. There is no square or cube or etc. And also, there is no product of the unknown function and or its derivatives. There is no multiplication between, for example, x of t times dx of t. Okay, so if these conditions apply, then we have a linear equation. So this is an example here. So dx by dt minus x of t equal to e of t. So this is called a linear equation. Why? First, all the derivatives and the function is to the power of 1. Okay, and there is no multiplication between the function and its derivative. This is also a second order linear equation, although there is a multiplication here, but the multiplication here is between the independent variable and the unknown function. Okay, so that's okay. Cosine of t, e of t looks to me like a nonlinear function, but doesn't matter. Okay. As far as these two conditions apply, then the whole ordinary differential equation is called a linear equation. So let's see an example of non-linear equations. Okay. So this is an example of non-linear equation. Why? First here, because we have cosine of x of t. Okay, so you are taking not cosine of t, but cosine of the variable that we have. Then this becomes a nonlinear equation. Here you have a multiplication of the derivative and the variable together. Okay, I'm not multiplying with t, but x of t, so this becomes also nonlinear equation. Here we have the absolute value, and also this is a nonlinear function as well. So here are the okay. So if we have something like this, and we want to find the solution that satisfies this. Now, we are not interested in this course to see how to solve the differential equations using closed form solutions. Okay, that's maybe you have covered that in other courses, or you are covering now. I'm not sure, honestly, if you covered this or I mean how to solve this, but that's not the issue, and I will not ask you to solve in a closed form a differential equation. But let's see, for example, here. This one is the solution of this is x of t equal to e minus t, and how we will reach this we don't care. Okay, but to prove this, if you take the derivative of x of t, it is minus e minus t. Okay, so if you substitute here minus e to the minus t plus e to the minus t equal to 0, so you satisfy the equation. So this is a solution for your differential equation. Now let's look to this. Same thing. Okay, so this is cosine 2t. Let's take dx by dt equal to minus sine 2 sine 2t. If I take the second derivative, the second derivative is equal to minus 4 cosine 2t. Now, if I substitute here, I will have minus 4 cosine 2t plus 4 cosine 2t equal to 0. So this satisfies. So this is actually the solution to this. The question is this a unique solution? Meaning, can I come up with something else that gives me or satisfy this equation? And as a matter of fact, yes. Actually, here, if we have a phase shift, it will not impact the derivative, and any constant that I might have here, I will have a solution. So it means that this solution is not unique, and that's something that is not good, because I will have an infinite number of solutions. I want to make sure that I will have only one definite answer, and to do that, for an nth number or nth order of differentiation, we need n conditions. So there should be some conditions. For example, here we have a second order differential equation. Then I will have two conditions, okay? And those two conditions will ensure that the answer that I will have is unique. So this is why in differential equations, you have to be given the initial conditions for the differential equations. And there are two different ways of giving you the initial conditions. And based on the information we give you, we have two different types of problem. The first one called initial value problem. And here, you will see that you have the initial conditions defined at one point of the independent variable. Here my independent variable is t, so I have x of 0 and x prime of 0. So the function has been defined and its derivative at one value of the independent variable, which is t here, which is 0 in this case. Okay, and also the other type of problems we call the boundary value problem. In the boundary value problem, we have given the initial conditions, okay, at two different points, but not at the derivative here, but at the function itself. Now, you will see that as we move on, that dealing with boundary value problems is harder than dealing with initial value problems. So let's see a practical example, engineering example of an initial value problem and a boundary value problem. Okay, so let's talk about here the circuit. The circuit here is initial value problem, where we need to have the voltage and the current in the inductor and the capacitor. Okay, and we need to know that at certain specific point. Okay, so we have, and of course, as we know that the current and the voltage in the inductor is that one is the derivative of the other. So I have to have two conditions defined here, because here I will have a second order differential equation, and to be able to have that, I have to have two initial conditions defined at the same time, which is usually defined at t equal to. Okay, so this is an initial value problem. Now let's look here to this interesting boundary value problem. Now this is a cross-sectional area of an underground cable. So here you have high voltage here, okay? Here you have ground, and in between the ground and the high voltage there is an insulation, okay? So all of this is insulation. Of course, this is needed to insulate the high voltage. This can be really high voltage. I'm talking about tens or hundreds sometimes of kilovolts, okay? So now, when we, as a designer of the cable, you need to know what is the voltage at these points. Very important to understand what is the volt. Why? Because I need to know the electrical stress on my material, and to make sure that my material can withstand this high voltage. Now, I know the high voltage at the boundaries only, okay? So I know the high voltage at this boundary, which is the high voltage of the cable, which is, for example, here this high voltage, example, this high 100 volt, and I know the voltage at the outside boundary, which is here the ground. The voltage here is equal to 0. The voltage here is equal to x kilovolt. Okay. So I know the boundary. Okay. Now what I don't know is the voltage in between. Now the equation that governs this is actually, this is a partial differential equation, but as I said, we will not go in detail. But here in this equation, knowing the boundaries, the two extreme boundaries, the high voltage and the ground, then I can find anything in between. So this is what I call boundary value problem, is that your unknowns is bounded by two boundaries that you already know the value, and you need to find the value in between. And we will have examples of the initial value problem and also the boundary value problem. Okay, so the analytical solution, as I said here, this is not the scope of this course. Now here we are more interested to find numerical methods to be able to find the solution for these ordinary differential equations. Now, the classification of the methods that will be used to find the solution of the ordinary differential equations, we have what we call single step methods and multiple step methods. Okay, so these are the two categories that we'll be using in numerical methods. The first one, which is what we call the single step method, it estimates the solution at a particular step. So basically, you are interested to find the solution. This is the solution that, for example, I'm interested to find the voltage as a function of time. Okay, so I need to find the solution at different time steps. Now, to find this, actually, you need to solve a differential equation, and then you will find the voltage at certain steps. So, for example, to find the voltage at particular step, you need the information of the previous step. Okay, so basically we start with the initial condition. This is my first step. I will find the voltage one step further. Then this new solution B now will be like my initial condition for the next step, and so on and so forth. So always I will need the information or the solution of the previous step to find the answer of the coming step. Now, multiple step methods, this is estimate the solution at, again, a particular step, but based on information of more than one step. So it's not just enough to know the previous one, but you need to know more information, and we will have examples of both